Okay, welcome back, students, to section 8.5. Okay. 8.5, oscillations of a mechanical state. Okay, so let's look at a spring mass system. Okay, so if I have a spring, okay, and then I have a weight on the end of that spring. Okay, and this is its natural length. Okay, we'll call this y equals 0. Okay. And then we pull that weight down past its natural length, okay, or its equilibrium state. Then this distance that it gets pulled down to excuse me. Okay, it's called L sub 0. And that's the displacement from equilibrium. We're going to say that down the positive direction. Okay, and we're going to call this a y of t. Y of t, and this is the mass. Okay, so there's some function that's gonna model the total forces involved in moving this thing a certain distance. Okay, and that function is going to be a function of y. It's the distance that we move the spring down. Okay. Okay, so we have a state of equilibrium. That we start with. And we have two opposing forces. Okay, first is the force due to gravity, okay, or F sub g, which is just mg. It's the mass times the acceleration due to gravity. Okay, but then we have the gravity going down. Okay, but we have resistance going up. Okay, so we call this F sub s. F sub s up there, there, and they're opposing each other, but they're in equilibrium because the weight or the mass is not moving. So number two is we have f of s, which is negative k times LO. Okay, so this is called the spring force. And the other one is called the force due to gravity. Okay, so we have gravity force and we have a spring force. Okay, and so we know that f of g plus f of s is equal to 0. Okay, those forces are in equilibrium. So if I add the two forces together, they're going to cancel each other out. And so I know that if I plug in mg plus negative KLO, that will 0, and I toss this to the other side, I get mg is equal to KLO. Okay, where K is the spring constant. Okay. Okay. FD is a damping force or force due to resistance. A FD is equal to negative C dy dt, where C is the damping constant. P is any external force, like a finger pushing down on the spring. F of T is any external force on the system. So the total differential equation that models the system is d2y dt squared plus d over m dy dt plus k over m y is equal to 1 over m f of t, where y at 0 is equal to y naught, and y prime of 0 is equal to v naught, right? Velocity at time 0. Where y naught is the displacement at time 0, and v naught is the velocity at time 0. Okay, solving this differential equation will yield two constants C1 and C2. Okay, omega naught is the circular frequency and it is equal to the square root of k over m. Okay, A naught is the amplitude of motion. And it is A naught equals the square root of those two constants, C1 squared plus C2 squared. Okay, and phi is the phase of the motion. And phi is equal to the inverse tangent of C2 over C1. Okay. Okay, that is, okay, A can be thought of as like R. Okay, and then the tangent of phi is like y over x. And so we could think of A naught as equal to C1 times the cosine of theta, or not theta, phi, sorry, phi. And A naught is equal to C2 times the sine of phi by using a little trigonometry. Okay, T is the period of oscillation and so T is equal to 2 pi over omega naught. Which was really equal to 2 pi times the square root of m over k. Okay, and f, little f, is the frequency of oscillation and that is f equals the reciprocal of this, 1 over t. Okay. Which is just omega naught over 2 pi or 2 pi over, or 1 over 2 pi times k, times the square root of k over m. Okay. Wait. Let's do an example. Example here. Mass 5 kilograms is attached to a spring with spring constant 5. It is stretched 1 unit with a velocity of 2. and a damping constant of 10. Okay, assuming no external forces find the circular frequency of the system. System amplitude, phase, and period of oscillation. Amplitude, phase, and period of oscillation. Okay, so first we need to solve this differential equation. Okay, so d2y over dt squared plus c over m, okay, y dt plus k over m y equals 1 over m f of t. Okay. So let's list out what we know. Okay, we know that c is equal to 10, m is equal to 5 kilograms, and then k is equal to 5, right? And f of t, okay, the external force is equal to 0. Okay, so I'm gonna go y double prime plus 10 over 5 dy dt. We'll just change these to y prime. Y prime plus k, which is 5 over 5, y equals 1 over 5 times 0. Okay. So y double prime plus 2y prime plus y equals 0. Okay, so now let's solve this using our differential operators. Okay, so this is going to become d squared plus 2d plus 1 of y is equal to 0. Okay, so let's factor this. This becomes d plus 1 squared of y is equal to 0. I can use my auxiliary equation to say that p of r is equal to r plus 1 squared, okay, which is equal to 0, and so r equals -1. Okay, with multiplicity 2. Okay, so because it has multiplicity 2, we have to take into account that this could be e to the negative t, or it could be te to the negative t. So our general solution is y equals c1 e to the negative t plus c2t e to the negative t. Okay. I'd like to solve for the constants, c1 and c2. Okay, we can do that with our initial conditions. We had initial condition of y at 0 equaling 1, and v at 0 is equal to 2. Okay. Okay, so if I plug in 0, I just get c1 equal to 1. So c1 is equal to 1. I mean, I could go through and show that. y equals c1 e to the negative 0 plus c2 times 0 e to the negative 0. This whole thing goes away, and that thing goes to 1, and this thing, and y is equal to 1. And so c1 is equal to 1. Okay, now I'm going to use my derivative because v at 0 is really just y prime of 0. Okay, it's just the derivative of the distance is the velocity. It's the change in distance over change in time. Okay, and so we have y prime is equal to negative c1 e to the negative t plus c2 e to the negative t plus, or minus, I should say, okay, minus c2t e to the negative t. Okay, and we want to evaluate that at 0. Okay, so if we plug in our zeros here, negative c1 e to the negative 0 plus c2 e to the negative 0 minus c2 times 0 e to the negative 0 is equal to 2. Okay, so this tells me that negative c1 plus c2 okay, is equal to 2. But we already know what c1 was. C1 was 1. So this is negative 1 plus c2 is equal to 2. And so c2 is equal to 3. Okay. So our general solution is y equals e to the negative t plus 3 t e to the negative t. Okay. With the c1 equaling 1 and c2 equaling 3. Okay, so now we're going to use some of this information about c1 and c2 to get the circular frequency of the system, the amplitude, the phase, and the period of oscillation. So let's do that. So omega is equal to square root of k over m. We kind of already knew what that was. That's the square root of 5 over 5, which is, so omega is 1. Okay. The amplitude is equal to the square root of c1 squared plus c2 squared. Well, that's just going to be the square root of 1 squared plus 3 squared, which is the square root of 10. So that's a naught. Okay, the phase is going to be phi, tangent of c2 over c1. It is equal to the inverse tangent of 3 over 1, which is the inverse tangent of 3. Okay, which is approximately 1.249 radians, approximately phi. Okay. And the last one, t, the period of oscillation is just 2 pi over omega. Okay, and that is just 2 pi over 1, so it's 2 pi. So the period of oscillation is 2 pi. Okay, let's talk about damping. The auxiliary polynomial E of R is equal to R squared plus C over M R plus K over M. It has complex conjugate roots. Okay, then the system is said to be underdamped and will be modeled as this curve. And we'll get a curve that kind of goes back and forth, but then eventually kind of fizzles out. Okay. Two, repeated real roots. Got in the last problem that we did. Then the system is said to be critically damped. Okay. Or okay, two distinct roots then the system is said to be overdamped. Okay. Or critically damped. And overdamped systems will be modeled by graphs resembling this guy here, where we'll start someplace, but then we'll end up, okay, still going to zero, but it'll never cross back. It'll never come back to its original spot. Okay. Okay, where there is at most one intersection with the t-axis. Okay, let's do one last example here. Number 2, determine the damping for the system modeled by d2y over dt squared plus 4 dy dt plus 7y equals 0. P of r, P of r is equal to, okay, r squared 4r plus 7, okay, is equal to 0. Solve that, that doesn't factor, so we'll have to use quadratic formula. Okay, r equals 4 plus minus square root of 4 squared minus 4 times 1 times 7 all over 2 times 1 equal to 4 plus or minus 16 minus 28 all over 2. It's going to be equal to negative 4 plus or minus 16 minus 28 is 12. Okay, so that's the square root of negative 12 over 2. So this becomes negative 4 over 2 plus or minus 2 times radical 3i over 2. So that becomes negative 2 plus or minus radical 3i. Okay, thus, r has 2 complex roots. And thus, the solution, the general solution, I should say, y of x is equal to, okay, and this is going to be, these are going to be complex, so that we're going to have sines and cosines involved, is equal to e to the negative 2t times c1 cosine of radical 3t plus, plus c2 times the sine of radical 3t. Okay, so that's the general solution. Thus r has 2 complex roots, and that's the general solution. Models a system which is underdamped. Okay, that is 8.5. Okay. I'll see you in the next video.